All right, now we're going to learn some basic relationships among the different performance measures. But before doing that, let's get familiar with the notations that we're going to use. Don't get overwhelmed with the number of notations we're using here, guys. Trust me, once you do 2 or 3 problems, these become very, very familiar for you. Okay, so let's start with that. Lambda, what's lambda? Lambda is the arrival rate. So here I have an illustration for a system like I used before. So where do you usually observe lambda? Lambda will be the arrivals, right? So for example, lambda can be, let's say it will be given as on average will be 15 customers per hour. Okay, this is an example. All right. Mu is the average service rate. So it's how many customers can be served by every one of these servers. All right, it's the service rate. So customers per hour or customers per minute, whatever. It's number of customers per time unit. LQ, this is the average number of customers waiting in line. Again, I turn your attention to this again. You can see all these are averages. All right, averages, because the system keeps changing, so you cannot have a performance measure that's constant. It keeps changing also. The number of people waiting in line, sometimes it's 0, right? Sometimes it's only 1, sometimes it's 2. In this snapshot, what do we can see? We can see that we have 3 here, right? So this is LQ in a snapshot. But remember that the LQ that we are referring to here, this is the average number of customers waiting. Okay, so LQ is always the average. LS, average number of customers in the system. Also, to have a better idea, in this snapshot, what's LS? Number of people in the system. In this snapshot, we have 6 people, right? Because we have 3 people waiting in line, 1, 2, and 3, and then we have 1, 2, and 3. They are being served, so we have 6 in total. Rho is the server utilization. Remember, we mentioned that before. It's how much time within, let's say, 10 hours working day, a server on average is busy. WQ, it's the average time that a customer will spend waiting in line. Okay, so only in that area here, what's the time that it takes on average also? Okay, remember this is changing, but it has an average of WQ. WS is the average time that you spend in the whole system. So from the time you arrive, and then you wait in the line, and then you go get served, and then you exit the system. All right, you go there, then you check your time. This is the time that you spend in the whole system. Let's say you ask all the 100 customers who came to that system that day, you ask every person what the total time that he spent, you divide by 100, this is your average, this is your WS. 1 over mu, this is 1 over the service rate. And remember, this would give us what? The service time, because service time and service rate are inverse. Okay, so this will be the average service time. Usually, just to let you know, usually we are given the service time, right? Because it's easier, or it makes more sense that you collect data about the service time than the service rate. And from service time, you can find your service rate, which is 1 over service time also. P0, remember we said that we're going to use the notation Pn, and we have specific attention to the case where n equals 0. That's why we have that P0. It's the probability of 0 customers in the system. Here also, in all probability equations, all the probability statements that we have in waiting lines, it measures the probability that we have 0 customers or n customers in the system. It's very, very important for you to understand that. Why that? Because I can ask you what the probability that we have 2 people in line, all right? Then I cannot use the formula that I have. I have to do some transformation that I will we're going to explain later. But just for now, you need to understand that these are probability in the system. Okay, then we have Pn. This is the probability that we have n person in the system. Then m is the number of servers. So in our case, what is our m? M is equal to 3, because we can see that here we have 3 servers. And finally, What is R? R is the average number of customers being served at any point of time. Okay. Now, in this snapshot, we can see easily that we have 3 people being served. Okay, but it's not always the case. Okay, so here we have 3, but as I showed you before that, at some times you don't see anyone here. And of course, if you don't see anyone here, that means no one is also here. That means I have 2 people being served. Or I can see that. So I have 1 person served. Or I cannot see anyone, which is P0, right? No one is in the system. So there are always either, if M is equal to 3 in this case, R, small r, can be either 0 or 1 or 2 or 3. That's it. It cannot be more than that because I don't have a 4th server. Okay? Now, we have some assumptions that you need to understand. Let me just erase these so that you can read well. Okay. These assumptions are always applicable to the models that we're going to learn. The first is the arrival has to follow a Poisson distribution, otherwise I cannot use the model that's available for us. Second is that the service time is also or follows also an exponential distribution. This is important. And the discipline is first come, first serve, and it's a single phase. Okay, we don't deal here with more than one phase. The second is that in order to use the models, the system should be underloaded. Okay, what does it mean? This is also very important. Remember, we said we have lambda is the average arrival rate. So in the previous illustration, I told you that I gave you an example that lambda is 15. Okay, and we have three servers. Let's say every server can serve 4 customers per hour. So this is mu. So my capacity, my system capacity is what? It's 4 times 3, 12. So this is my capacity, while demand, which is my arrival rate, is 15 per hour. So I'm already overloaded. For such case, I cannot use the models. Why? Because in such case, the line will keep increasing and increasing. It will not decrease. All right. So to be able to use the model, I should have at least 4 servers in this case. If mu per server is given as 4, so then my total capacity will 4 times 4, 16, which is greater than 15. Then my system is underloaded and I can study it. Finally, the arrival and service rate should be uniform. They cannot change with time. All right, so this is an assumption. You don't need to worry about that because these will be embedded in the models that we're going to learn. All right, now that we are familiar with the notations, we're going to examine some basic relationships. What do you mean by basic relationships? That means no matter what model we are, no matter what the system that we have, okay, these relationships are there. Why this? Because these come from logic. Okay, it's not because of the nature of the model itself. So server utilization. Okay, remember we defined that as the percentage of time a server will be busy. This will be denoted as rho, as we saw before, and this is equal to always lambda over m mu, where lambda is the arrival rate, m is the number of servers, and mu is the service rate. Okay, so this is done. Second, the average number of customers being served at any point of time. Remember in the previous diagram we saw 3 people being served, so this is R, and R is always equal to lambda over mu. Okay, by the way, in most of the functions, most of the formulas that we're going to use, you will see that ratio lambda over mu. That's why when we start doing the problems, I'm going to tell you that whenever you find lambda, and you immediately find this ratio lambda over mu, because then you can plug it in the corresponding formula. Average number of customers waiting for service, this is LQ. Okay, this one we don't have a general formula for it because it depends on the model itself. So that's why we need to wait. Whether we have single server, LQ will be different than the case when we have multiple servers. Number of customers in the system, this is LS, and this is related to LQ, right? We have seen that graphically. We could see the relationship between LS and LQ, where LS is number of people waiting in line, plus those being served, right? Which is lambda of mu. Here we go, which is this one. Okay. Then average time a customer wait in line. This is WQ, and this is always equal to LQ over lambda. All right. Now, average time a customer wait in the system. So here we can find that in two methods. Either it's equal to LS over lambda, so it's very similar to this one, but now it's LS over lambda, or it's equal to the time that you spent in line plus that. What's that? 1 over mu. This is our service time, right? Remember, these two measures are inversely related, service time and service rate. So 1 over mu is service time and 1 over service time is mu. Finally, because we have lambda and mu in a ratio, certainly the time a unit used in lambda should comply with the time unit of mu. So if one is not similar to the other, you have to convert one. For example, if you are given lambda as arrivals, number of customers per hour, and mu is given per minute, you have to change one of these. And finally, these basic relationships apply for the two models, the single and the multiple. So in addition to the formulas that will be specific to the models, we can use these basic formulas at any time. All right. So even if you don't know what model you have in hand, you can use these basic relationships, as we're going to do, in fact, in the next problem.